Hello, I am Marcos Lupion and I will present the work entitled Parallel Pipeline for Adaptive Synthetic Data Augmentation in Thermal Imaging Pose Estimations. My colleagues are Juan Francisco San Juan, Vicente González Ruiz and Pilar Martínez Ortigosa from the University of Almería. This is the outline that we are going to follow during the presentation. First of all, we are going to give a little introduction to the topic. Human pose estimation is the computational process of detecting and localizing human joints and body segments in images or video sequences. These key points serves to interpret the human movement in computer vision and deep learning approaches. The human pose estimation using visible cameras is very optimized nowadays since we have high resolution but low privacy images. They can capture facial features and identifiable information, which can raise significant legal and ethical concerns in sensitive contexts such as healthcare, surveillance, or domestic environments. So the solution is to provide low-resolution thermal cameras. One of the advantages is that they can preserve the privacy as they do not show identifiable details, and they can detect human presence and movement through temperature contrast with the environment. The challenges are their low resolution, which makes accurate human pose recognition a difficult task. Also, the lack of labeled thermal dataset limits the training of deep learning models. The techniques for obtaining the human pose on the thermal domain can be, for example, the manual annotation. We have full control over the data which are annotated, but the main disadvantages are the time and resource intensive consuming and also the poor generalization capabilities on new environments. So one of the solutions to this is the using paired images annotations. Having both thermal and visible images, the labeling is performed on the visible one and the annotation is written or is used in the thermal image. One of the main disadvantages of this is that it requires both visible and thermal cameras, which can be expensive and less accessible equipment. So one of the proposals in this work is the use of synthetic data as an alternative. The synthetic data increases the amount and diversity of data without requiring manual annotation. Having the original thermal images, generating some synthetic data similar but not the same as the thermal images, we can augment the dataset and have more annotated thermal images with the poses. Most of the techniques that are used to generate synthetic data are generative adversarial networks and probabilistic diffusion models. So we are aiming to apply the generative adversarial networks into this problem. In the theoretical and technical background, we have the generative adversarial network, which were introduced by Ian Goodfellow in 2014. It consists on two neural networks, a generator which generates some realistic data similar to the data that we have in the dataset, and a discriminator which tries to determine if the data that the discriminator is seeing or receiving is from the generator or the dataset. So in this neural network, play a min-max game. Each of one tries to optimize itself and make the other network worse. So a particular case of this is the style gang architecture, which was developed by NVIDIA. In the key innovation of this style gang architecture is the style-based generator, which enables a control over the visual features at the different scales. However, the generative adversarial networks may suffer from overfitting when trained on very limited data. Traditional data augmentations, by having fixed policies, may harm the learning dynamics of this network. So ADA, adaptive data augmentation, was proposed in StyleGAN 2. It introduces adaptive augmentations like flipping, rotation, or color jittering applied to both real and fake images. The strength of the augmentation is dynamically adjusted based on the discriminator performance. So the adaptive data augmentation monitors the discriminator confidence and increases augmentation only when overfitting is detected. In our case, the proposed evaluation metrics for the problem is the percentage of complete poses detected in the synthetic images, which allow us to measure the degree of structural coherence and realism in the generator. So the OpenPose framework, which obtains the pose from the thermal images, and the adaptive data augmentation are applied to generated images. Then we quantify the pose accuracy of the generated images, and then this information is used to train the discriminator and generator neural networks. So the GAN is adapted to the task of human pose recognition. As we mentioned, we are using the OpenPose framework, which is a 2D human pose estimation neural network in multi-person scenarios. It detects the key points of the human body using the COCO dataset. In the thermal images, it struggles in low resolution and low contrast due to the lack of domain-specific training. In our workflow, it serves as a reference to guide the synthetic generation of the thermal poses. Here we are going to present our proposal, the StyleGAN 3 pose. Here we can see the architecture of the generator based on the StyleGAN 3 from a latent space Z transformed into WB by a mapping network. It adds some Fourier feature to keep the spatial coherence. The generator has 14 convolutional blocks with some outputs to RGB in different scales and operations like modulation, convolutions, and activation, linear and non-linear. This is the schema of the generative and of the GAN process. From a latent space and some noise, the generator generates some fake data representing the synthetic thermal images. Then the adaptive data augmentation is performed in this data as well as in the original training dataset, and the discriminator network tries to determine if the images that it is receiving are true or false. Then this error is used to train the discriminator and the generator. Our contribution is the integration of the structural feedback of the human pose recognition. So once the synthetic images are generated, OpenPose is used to determine if there is a pose in the image. This information is feedback to the discriminator network, which is then retrained using or trying to maximize the poses or the images that determine the poses. So this module allows the generator networks to produce more realistic synthetic images. Here we can see the distribution of these architectures or of this schema into the GPU and CPU. The main part, the GAN part, is performed in the GPU, and the evaluation of the synthetic images is scheduled into the CPU. Well, here we can see the parallel CPU-GPU execution. So first one, the dataset is loaded using the CPU. Then this data is transferred into the different neural networks to generate the images and classify the images in the discriminator. And then once the synthetic images have been created by the generator, the CPU executes the OpenPose network to determine if there is a pose on this or not. And then this information is fed back to the discriminator, and then the GPU continues its execution. So we have two parallel branches, one of them in the GPU with the GAN approach, and then in the CPU with the validation of the pose extraction of the synthetic images. Here we can see the proposed stopping criterion in order to determine the optimal training point of the GAN, since in the GAN there is no early stopping or similar, but the user has to determine when the training has been finished. So here we propose a stopping criterion of using the standard deviation in less than 4% in the percentage of human pose detected. Here we can see the percentage of generated images. We detected full poses and highlighted the stopping criterion of the different datasets. Now we are going to describe the smart home dataset and the preprocessing strategy that we follow. Well, to record the images, we used a Raspberry Pi with a thermal camera. The thermal camera model is the FLIR Lepton 3.5. It's embedded using the Pure Thermal 2 Smart I/O module, and these datasets are recorded in the Smart Lab of the University of Almería. This camera records in 160 per 120 pixels, and several configurations are recorded. The first one is facing backward or onward with 33,000 images, more or less. And then it was changed by incorporating some chairs or hiding some part of the body. And we have to 2,500 images more, up to 25,000 and a half images. For all of them single person images. And then a more complicated or hard dataset incorporating 2 and 3 person overlap, which consists in 3,451 images. So we are testing with the different configuration of the datasets. OpenPose is used to determine if the pose is obtained in synthetic thermal images. We can see here the 3 different configurations. One of them, no detected pose. The pose is not detected on the thermal camera. The second one is a sketchy pose, which determines half of the pose, maybe some parts like the legs are not recognized. And finally, the full pose, that it's the configuration or the situation that we want to maximize in our dataset. As for the experimental results, we have here the distribution of the CPU and GPU usage in this training loop. We have 5 stages. First one, loading the initial network snapshot. Second one, the training. Third one, the creation of the synthetic images. The fourth one is the detection of the human pose. And the fifth one is the network snapshot. As we can see in the CPU is underutilized in all the process, except when the GPU finishes its execution. The GPU is performing creating the synthetic images, training the dataset, and saving the network snapshot. And the CPU is mainly used for detecting the full human pose using the OpenPose. As we can see, first is used the GPU. Once the GPU finishes, it executes the CPU in the original approach, in the StyleGAN 3 training. In the sequential training of the StyleGAN 3, we can see that first the GPU loads the initial network snapshots, train the synthetic approach, creates the synthetic images, and then it goes to 0, no use the GPU. And then in this point, the OpenPose and the CPU is executing OpenPose to determine if there are some poses in the synthetic images created by the generator. So the GPU is used, generated the images, then the CPU is used to execute the OpenPose, and then this is a sequential process. This is the sequential version. Well, finally, the parallel version executes all the process, and while the GPU is being used to train the networks and generate the images, the CPU is being used, as can be shown. Here we can see the training statistics for the StyleGAN tree models without using the adaptive data augmentation. We can see that in all the cases of the datasets, the least number of pose is the 12% and the maximum the 41% of the full pose in the different configuration of the datasets. Here we can see the approach, but using our proposed approach. We can see that in all cases the full pose represent more of the 70% of the images of the dataset. So, and we can see with the RTDS the reduction in the time used to train and generate the images and train the whole system. So we can see better results, and with the parallelization approach we can see a reduction by more than a half of the times the dataset. Here we can see more clearly the improvement with the StyleGAN tree pose customized with the OpenPose detection of the pose to further fine-tune the discriminator. So we can see clearly that our approach is working. In conclusion, a parallel pipeline based on StyleGAN tree pose has been presented for the generation of synthetic thermal images with complete human pose, aimed at improving human pose estimation. The integration of structural feedback through OpenPose and adaptive data augmentation has enabled the selection of synthetic images with detectable poses, significantly enhancing the structural quality and coherence of the generated samples. The StyleGAN tree pose model, combined with the adaptive data augmentation approach, doubles the detection rate of full human pose in synthetic thermal images compared to the original model, reaching values above 80%. Experimental results show a substantial improvement in the percentage of detected full pose compared to the conventional StyleGAN tree training, with training time savings exceeding 50% in several well smart home dataset subsets. As far as future work are concerned, implementation of a dynamic strategy for the automatic selection of snapshot intervals will be carried out for more precise monitoring of the optimal stopping point. Additionally, we propose exploring the reinforcement self-annotation techniques using reinforcement learning or active learning in order to further reduce the reliance on manual annotation or RGB thermal image pairs. Thank you very much for your attention.